Today we're going to learn about determining intervals of concavity. Let's say we have a problem like this. Determine the intervals on which f of x is concave up. So, we remember that concavity has to do with the second derivative. So that means that we should first take the second derivative. So the first derivative would be 12x to the third. Let's use a darker marker. So the first derivative would be 12x to the third minus 60x squared. And that would mean that the second derivative would be f double prime of x, which is equal to 36x squared minus 60x. So before we can find where the domain of f of x is concave up, or where f of x is concave up and concave down, we have to first find out where the inflection points are. So we remember the inflection points are where the concavity changes from negative to positive or positive to negative. So that means that it's a root that's not a double root. So that means that's a root that passes through the x-axis. So let's find the root of f double prime of x. So the root of 36x squared minus 60x, so we can set this equal to 0. So that means that x times 36x minus 60 is equal to 0. So that means that x is equal to 0 and 36x minus 60 is equal to 0. So that means that x is equal to 0 and 36 minus 60. So that means that 36x, and this was supposed to be 36x. So 36x would have to be equal to 60. So that means that x would be equal to 60 over 36. We know that these are both divisible by 6, so we get 10 over 6, which is equal to 5/3. So, now that we have our inflection points, so these are inflection points, you can take a moment to look at how we did this before we start the next half of this problem. So now that we have these points, and actually these are not inflection points, these are possible inflection points. Let's write that down. They're not just inflection points, they're possible. And they're possible inflection points because this does not take into account whether these are single or double roots. So the next step is to determine whether these are possible or whether these are inflection points or not. So to do that, we have to use a sine line. So let's draw a sine line. We know that this is the sine line of f double prime of x. Let's draw this a little lower because we need more space. So let's draw it here. And the sine line is useful because, one, it determines whether it would help you determine whether these are actually inflection points or not. And it also tells you the interval on which something is increasing or decreasing. So in this case, it would tell you the interval on which f of x is f double prime of x is increasing or decreasing. And if you know the intervals on which f double prime of x are increasing or decreasing, then that means that you know the intervals on which f of x are concave up and concave down. So let's put these 2 points down in their order. So one thing about sine lines is the order doesn't really, or sorry, not the order, the spacing between the 2 points doesn't really matter. So this is 0 and this is 5/3. So the spacing between these 2 points or 3 points or 4 points and so on does not really matter. You just need to have enough space that you can write the signs between them. That's why it's called a sine line. The signs are plus or minus, obviously, positive and negative. So we know that the sine line would extend to negative infinity here and would extend to infinity here. So now let's list down the factors that we have. So the factors of f double prime of x are either just this one factor here, or you can split it up into 2 different factors here. Now, the more factors there are, the better, because that's when it becomes more simpler for us to do the calculations. So this form, because it has 2 factors, and it's its most simplified form, or close to its most simplified form, would be more useful than this one. This would be harder to use. So the first factor would be 36x minus 60. 36x minus 60. And the second factor would be x. Let's move this over a little bit so we get some more space on the left. Whoops. I'll just redraw this. So this is f double prime of x, the sine line of f double prime of x. This is the point, or the x value of 5, 3, and this would be 0. So I moved it over so that we have enough space on this side to write the signs in. So let's say we have a number that is less than 0. We know that all the numbers less than 0 will be negative, right? Now let's just pick a number between 0 and negative infinity. Let's take negative 1, for example. So if we take negative 1, and we can take, this will be true for anything on this interval from negative infinity to 0. It's an open interval. If you take, this will be true for any of those values, so if you take any of those values, let's say negative 1, then negative 1, let's say this is the x value, when we plug it into these 2 factors, we get the top factor would be negative 1, which is a negative factor, or negative. When we plug it into here, we get 36 minus 60, which is obviously, or it's negative 36 minus 60, which is obviously negative. So we can see that these 2 are both negative. And let's just go and make sure that this would be true for anything on that open interval from negative infinity to 0. We know that a negative number will be negative. We also know that a negative number times 36 is negative minus 60, which keeps it negative. So we know that this will always be negative. So now let's move on to here. So instead of finding a point between these 2 values, or finding a point on this open interval, let's do what we did the second time and just analyze it. You could always use a point, but let's say we had a fraction like this, 5/3. We could just use 1, but if we had a smaller fraction, it would be harder to find a value that would be easy to compute. So we know that a value between 0 and 5/3 will be positive. So if this is positive, then that means that this top factor will be positive. Now we also know that for the bottom factor, if you plug in 5/3, then 5/3 times 36 is 60, minus 60 is 0. That's why it's one of the inflection points. So that means that any value between 0 and 5/3 will have to be negative, because a value that is less than 5/3 will have to be less than 60. And if a value is less than 60 and you subtract 60 from it, then it's negative. So this will have to be negative also. If we plugged in a number between these 2 values on this interval, let's say 1 for example, then we would get 36 minus 60, which is negative. So that supports our claim. And then we have the last one. So anything from 5/3 onwards. So we know that this will still be positive. So the top is positive. and the bottom factor, we know that this is greater than 5/3, and we know that 5/3 times 36 is 60. So that means that any factor, or any number, greater than 5/3, when multiplied with 36, would be greater than 60. And if a value is greater than 60 and it has 60 subtracted from it, then that means that it's still positive. So we could just say plus here, because all of those values will be greater than 60 when it's multiplied with 36. Let's take, for example, 2. When we multiply 36 with 2, we get a value that's greater than 60. That would be 72. 72 minus 60 is 12. So now the last step. Now that we have all our signs down, we just have to multiply them with each other. So when we multiply these two, negative times negative becomes positive. Positive times negative becomes negative. It's negative. And then positive times positive remains positive. Now one thing to keep in mind is just a simple computational error, is if you have 3 negatives, then that's still negative, because then you have negative times negative, which is positive, times negative, which is negative. So just that one thing to keep in mind, when you have an odd number of negatives, it's still negative. But when you have an even number of negatives, it's positive. Anything that has plus and minus in it, like a pair like that, would have to be negative. And we know that any amounts of any number of positives will always be positive. So let's look at what our sign line is telling us. Our sign line is telling us that on this interval, the second derivative is positive. On this interval, the second derivative is negative. And on this interval, the second derivative is once again positive. And I apologize for before when I said that the sign line for f double prime of x will tell us when it's increasing or decreasing. When f double prime of x is increasing or decreasing, it doesn't. It actually tells you when f double prime of x is greater than 0 or less than 0, or it's positive or negative. So we know that f double prime of x is positive on this interval, negative on this interval, and positive on this interval. So we know that f double prime of x relates to concavity of the graph. So that means that on this interval, from negative infinity to 0, and these are all open intervals, keep in mind, the graph would have to be concave up. On this interval, it would be concave down, and on this interval, it would be concave up again. So let's write down these intervals. So hopefully you understood this part by now, because now I'm going to erase it. If you didn't get it, you could go back in the video and pause it and look at it. So, the answer to this problem would be concave up on the interval. And you probably want to write this in a sentence too, just to be safe. But for this we're not going to, because it's just a video. So it would be concave up on the interval of negative infinity to 0, union, or that also means also, it would be concave up on the interval from 5/3 to infinity. And the union sign means and, not also. Or and also are the same thing. And it would be concave down on the interval from 0 to 5/3. So a sentence that we could use for this problem, and the answer would be, the graph is concave up, or the function is concave up, or you could say f of x is concave up to be more precise. So f of x is concave up on the intervals negative infinity to 0 and 5/3 to infinity, and f of x is concave down on the interval, on the open interval, from 0 to 5/3. And these are all three open intervals because they have parentheses instead of brackets. Today we learned about determining intervals of concavity.